Cool. So, hi everybody. My name is Zachary Brown. I'm a lead data scientist at S&P Global Market Intelligence. Actually, I am officially a part of S&P Global Corporate now. Who's familiar with S&P Global, like Standard & Poor's, like the S&P 500? Cool. So I don't work for that part of S&P. I work, like I said, I work for a division of S&P, which was formerly called Market Intelligence, and now they've rolled our machine learning capabilities into corporate. But what S&P Market Intelligence does is it takes a whole bunch of data that's freely available online, like public filings for financials of different companies, or public filings in the energy sector, or a whole bunch of different places, scrapes all of those from whatever publicly available sources they have, and then processes those through a really highly refined curation pipeline. And then we make that data available in a variety of ways. So one of our traditional ways for customers working with our data products would just be through a website that we have. So we have a web product called Market Intelligence that you can just go to, and you can do all your searches and figure out what stocks to buy, what stocks to sell, et cetera. We also offer our data through things like Excel plugins. You can just load your data right into Excel, or for the data scientists in the room, things like RESTful APIs. You can just get a straight fire hose of data that you're interested in. Now, our traditional model for the past maybe 20 years or so was, I mentioned that we pull data from public sources, and then we have content curation pipelines where we take that data, process it, pull all of the useful information out, and then make that available in our product. For the past 20 years, that whole process has been largely manual. So we would build internal products that facilitate the extraction of data from different document types by hand. So we would have analysts reading through documents in some sort of a Java application, and they're typing out like, this is how much this stock was worth on this day, or something like that. And we don't really want to do that anymore. We can use data science to optimize a lot of that stuff, and then free up our analysts to work on the harder things that data science can't necessarily do. So that's where my team comes in. I work on a fairly small department. I think that we have 14 data scientists now, a couple machine learning engineers. I was number 7, and I've been there for about 2 years, so we're growing pretty quickly. In terms of S&P Global as a whole, we have like 250 data scientists across all the divisions, so ratings and indices, things that you might be more familiar with. But our division is particularly focused on our content curation and content collection pipelines. So all that's my long-winded way of saying we do deal with a lot of semi-structured and unstructured data at work. And today I'm going to talk through some of the different processing techniques that you can use for this type of data. So you can think of like a business filing, like a 10K or something from a company, is just a PDF or an HTML file or something, and that has a whole bunch of tables in it that we might want to extract data from. It also has a lot of information that we generally want to capture available in free text, and that's where some of the things that I'm going to talk about today come in. So how do we take just free text and find value in it and model that free text in a whole bunch of different ways? So just a show of hands, who has done any sort of natural language processing before? All right, lots of you, cool. I'm sorry if the first part of this is boring. Who has done deep learning actually just who has done deep learning in general before? All right, a good portion of you. Who is, what is the intersection of those two groups? Who has done deep learning and NLP? All right. If you've done really, really deep stuff, this talk may be a little bit boring. If you haven't, then I'm going to take you like from the beginning of like, what does NLP look like? What do different NLP processing pipelines look like? What does machine learning for NLP look like? And take you all the way to what does a neural machine translation model look like? How do I do part of speech tagging using some fundamental elements in deep learning? So some fundamental types of neural nets. So a basic outline of the talk, I'm going to just give an overview of what a typical NLP problem looks like. Then I'll walk through text classification, and I'll use an example use case of a perceptron. So before getting into more advanced stuff with neural nets, I'm just going to walk through exactly how you would build and execute a neural net using a framework called PyTorch. Then I'm going to talk about vectorization and classification with RNNs, and I'll finish up with part of speech tagging with RNNs. If we have time, I'll get to sequence modeling, but this talk, when I give it, usually lasts about 2 hours, and we have about an hour and a half. So we'll see if we get there. If you want to ask anything about that, I'll stick around for a little while afterwards, and or all of the information is available on GitHub like I showed you. So let's dive right in. So what does a basic natural language processing problem look like? I would argue that it looks something like this. And for those folks that are heavily into NLP in the room, don't judge me on my oversimplified view of what an NLP project or problem would look like. But I would argue that at a high level, you could say that you start out with some document or some text in general. It could be like a full text of a PDF. It could be just like a tweet. It could be anything. You walk through some sort of vectorization process to produce a vector that can be used for input for a machine learning model. You then run that vector through some sort of a task, and you produce some sort of an output. That output is itself can be seen as a vector of different types of numbers. So that output changes depending on your particular task type. So let's say that you're going to do binary document classification. You take your whole document, you vectorize your document, you get a vector, you feed your vector into your machine learning model, and that produces just a single value, just a scalar value that usually represents the probability of that document being one thing or another. Another way to think about this would be everything up until the task stays the same, but instead of outputting just a single number, now we're going to output a vector of several numbers. And these numbers might stand for probabilities that a document is one of a multitude of classes. So you might have multi-class document classification. Additionally, you could have multi-class sequence classification, and this is where things start to wind off a little bit from your traditional machine learning models, because now your vectorization process isn't just going to produce a single vector that you then want to classify. Your vectorization process is likely to produce a multitude of vectors, and you want to run some classification or have some downstream task operate on one or all of those different vectors. So we're going to start out easy here. We're just going to talk about a neural net, and we're going to use traditional vectorization for our neural net. So we're going to use something called a TF-IDF vectorizer. This is just a count-based vectorization approach where, in essence, we just take a whole document and we count up how many times a word occurs in that document, and then we call that the number for that particular word in the document. So you can think with that type of vectorization, you probably have really long vectors because you have to have a different element in your vector for every single word, and we'll just ignore that fact for now. We're going to implement a perceptron binary classifier, and that is going to take in a vector, our TF-IDF vectorized document, and just output a single number. And for this, we're going to use a framework called PyTorch. So I know lots of folks have used TensorFlow. TensorFlow is pretty popular these days, especially with the Keras front end. Has anybody in the room used PyTorch before? All right. All right, so you're going to get a little bit of exposure to PyTorch in this session. The reason that I like PyTorch, I actually really like things like Keras and TensorFlow, especially Keras, for quick prototyping. And a lot of times, if I want to just try an idea out really, really quickly, I'll just use something like Keras. I like PyTorch because as I got deeper and deeper into deep learning and building my own very modular deep learning algorithms, you're kind of forced to set all of the parameters by hand, so you really have to think through all the decisions that are being made, and there's nothing obfuscated from you. So I like PyTorch, and you'll see a little bit as we walk through the notebook. I'll call out some of the reasons why I actually really like PyTorch, because it makes it really easy for debugging as well. So let's get started with text classification and the perceptron. So here, I'm just going to give an overview of what a perceptron is and talk about how we actually do neural net optimization, and then we'll hop right into an example in a notebook. So this is what a perceptron looks like. I actually have an updated diagram where I remove that summation box and where I split out the summation and the sigmoid, but just for the time being, just think of those as two distinct operations. So what we have here is we have all of our data input on the left, so you can think of this as your vectorized version of a document, or these can just be your features for any sort of simple classification in machine learning. And then each one of these lines in this diagram represents a weight in the model that we want to learn. So as we pass data through the model, if we want to run inference or something, we take all of these values for a particular input vector, we multiply them by the weights, and then we sum them. And then because we want to do classification here, the output of that summed vector is going to just be a floating point number, an unbounded floating point number. And we want to do classification, so what we're going to do is we're just going to squish that down using a sigmoid function. So that's going to reset the bounds or squish down the bounds of that floating point output to lie between 0 and 1. So then we can interpret that thing as a probability. So this y hat here would just be a number between 0 and 1. So we take all of our data, multiply by our weights, sum that all up, squish it down to between 0 or 1, and then that gives us our prediction. So what we want to do is we want to optimize these weights based on some known labels that we have. So how do we actually carry out that optimization? Well, first we need to define some sort of a loss function. So some function, it can be an arbitrary function. There are several that are typically used for binary classification. And we calculate the loss, so how off are we? How much are we wrong between the true answer, represented by y here, and then our probability of that particular class as output by our model. So we have some sort of a loss function defined. And then what we do is we use something called gradient descent. So what gradient descent does is it says, well, how much did each one of the weights that we have in our model contribute to our wrongness, contribute to the overall loss that we had? So the way to do gradient descent is calculate the derivative of that function with respect to each one of these weights. And then you have to update your weights. So you subtract off a little bit of each one of the weights to make you more right on the next pass. And here, for each one of the weights, the updated weight is the old weight minus that derivative, which gives you the contribution of that weight to your overall loss. And then that's multiplied by something called the learning rate here. So how quickly do I want to move through the parameter space to the right, to the optimal weights? So that is all of, that's all of backpropagation. Like everybody talks about, I've read a lot of blogs that kind of treat backpropagation as this mysterious thing, and it's really straightforward. You're really just taking derivatives of things, and for complicated networks, yeah, you have to keep track of what all of these weights are and their interconnected dependencies, but frameworks like PyTorch and TensorFlow do all of that stuff for you, and all you really have to do is know what the high-level steps are. So you do some sort of a forward pass to produce some prediction, you calculate your loss, you calculate your gradients with respect to that loss, and then you update your weights. And we'll actually walk through code that just does this for a single example so you can see how it actually works under the hood. So I'll just drop out of my slides here and jump into a notebook. Can everybody see that okay? Yeah, folks in the back, should I make it a little bit bigger? No? All right, we're good. So to start out, we're going to start out with just importing a whole bunch of different packages. So I'm importing Torch here, I'm importing NumPy and Pandas, and then I'm importing some different things from torch.nn. Torch.nn or neural net contains all of your different modules that are just, you can think of them as your building blocks for building complex modules in Torch. Then from the Optum package, I'm going to import stochastic gradient descent. This is going to be our optimizer that we're going to use to execute stochastic gradient descent. I'm going to import a couple of different loss functions for different tasks that we're going to look at, and then I am going to import my poor man's tokenizer, my poor man's tokenizer friends, and just some other Python-related things. For our TF-IDF vectorization, I'm going to use scikit-learn's TF-IDF vectorizer, and then I'm going to use train test split and accuracy score to figure out how well we're actually doing here. So for this particular use case, we're going to use a prepared version of the Stanford large movie review data set. So this is an openly available data set that I think contains 50,000 examples of movie reviews, and then the associated sentiment, positive or negative for that. This particular data set is really useful for demos like this because they specifically chose highly polarized reviews. So you don't have anything in that gray middle ground of like, is this positive or is this negative? It's highly polarized. You have very positive things and very negative things. So it should train pretty quickly. I'm just training on my laptop with no GPU here, so that's what we're kind of after here. It contains, like I said, 50,000 highly polarized movie reviews from IMDb, and we're just going to do some minimal pre-processing to start. So here I've just defined a function. So I'm just reading in a pickle file that I have previously, and then I'm just going to define a function called clean text, which just lowers your text, removes all punctuation, and then joins it back together. So super, super simple. Please don't, I don't think that any of my colleagues from S&P are in the room. If you see them, please don't tell them that I do stuff like this. You usually want to do much better tokenization, but for this is all, I mean, this is good enough for what we're looking at. And actually, in reality, when you're dealing with neural nets for natural language processing, I tend to go with minimal pre-processing, at least as a first pass, and then you can go back and say, well, I had all of these issues with these particular bits of punctuation or with these particular phrasings of things. You can go back and clean stuff up, but I usually try things at a first pass with just very minimal initial prep. So for my text vectorization, I mentioned that we're going to use a TF-IDF vectorizer. And sorry, I'm just going to scroll up and execute these cells. We're going to use a TF-IDF vectorizer. And all I'm going to do, sorry, this is what our data looks like after we've loaded it in. So we have text, and then we have text cleaned. You can see that I've just removed punctuation and lowercased all of my data. And then we have a label, which is just a 0 or a 1. So really straightforward. We're just doing binary classification. So for vectorizing, I'm going to instantiate an object of a TF-IDF vectorizer, and then I'm just going to fit all of that and spit out the total number of tokens in our input corpus. And this is going to be a lot of tokens. In this set of 50,000 movie reviews, there's a whole lot of distinct words there. So I'm actually just going to cap that at 1,000 of the highest frequency words just for the sake of this particular demo. This is one of the things that I don't like about traditional count-based approaches is that you have to, like, you have, let's say, 20,000 words in your corpus. So your naive representation of a single word in that corpus or a single document is going to be a vector of length 20,000. I don't like either dealing with vectors of length 20,000, even if they're sparse representations, or capping that, because if you cap that to a particular value, like I'm doing here for the purposes of this demo, then you're necessarily enforcing some sort of information loss. You're just throwing away some information that could be useful. Now, getting rid of things like stop words, getting rid of the, and, but, whatever, that's different from actually just truncating, saying these words don't occur often enough, and I'm just going to throw those out. So that's why I try to stay away from typical count-based approaches when I'm worried about more fine-grained details of my particular data set. But for the time being, we're going to ignore all of that. So I'm going to set my maximum features to 1,000 and then rerun my TF-IDF vectorizer, convert it to a dense matrix, reshape it so it's an appropriate shape to run through our PyTorch model, and then I am going to run a train test split. So this will take just a second to run, and in the meantime, it actually will spit out how many words were in the original corpus, so we can see how much stuff we're actually truncating by just limiting to 1,000 features. So I was actually wrong. I thought that it was 18,000, but there's 180,000 distinct tokens in this corpus, and I'm limiting to 1,000. So sometimes you might do this for computational reasons or just because the data set calls for it, but you're chopping off quite a bit here. So we'll get back to how you actually might not have to chop all of that stuff off a little bit later. So now let's look at actually implementing that perceptron classifier. So here we have a whole bunch of different things here. So this part right here, all of these weights, These are going to be stored in something called a linear layer. So all a linear layer does is perform a linear transformation on your data set. So you have a vector. You can think of a linear layer as just being a matrix of a whole bunch of different weights. So you multiply your matrix onto your vector, and that produces another vector as output, and then you just sum over all of the output values for that. And then you squish them down with a sigmoid. So all of these things are just in PyTorch. So we're going to first create a linear layer. The input shape is going to be max features. That's that 1,000 dimension vector that I had before. And then because we only have just a single linear layer, we're not passing this through anything else, and we're doing binary classification, my output shape is going to be 1. So I just want to output a single one-dimensional vector there. And then I'm saying bias equals true. I want to add on an additional bias term for this classification. You can disable that if you want. Then I'm going to create an instance of the sigmoid function. So this is just a sigmoid function that knows how to operate on fundamental torch objects, and it will operate element-wise on all of those. Then I will create an instance of the binary cross entropy loss function. All this does is calculate the binary cross entropy between a single 1 or 0 and then a probability. So this just measures how wrong you are from what you expected. And then, like I said before, we're going to use stochastic gradient descent to optimize this. And because this is an optimizer, it needs to know what specific things to optimize. So we are going to pass in for the parameters that we want it to optimize our linear layer, this guy up here, dot parameters. And we're just going to specify our learning rate, that little L that you saw in my update to my weights, at 0.01. So no magic going on here at all. All I've done is just create a whole bunch of torch objects. Now in this cell, this is what as I was learning PyTorch, this is what I did for almost every single project that I did. And I thought that it was really, really useful to just be able to pass my data through each individual object that I created and look at the shape of the output. See if I'm using these things right. See if all of the assumptions that I just walked through in those slides make sense. So I'm going to just walk through this bit by bit, and as I pass data, my first 1,000 dimensional vector, through each one of these things, we'll look at the shape and look at the values of each one of the outputs. So here I'm just going to be commenting things out. The first thing that we do is just grab an example of features and an example of labels, and then I'm going to cast those to torch float tensors. So a torch tensor you can think of as being completely analogous to like a NumPy ND array or something like that. So they can it's just an array with an arbitrary number of dimensions. They can get, I think you can have like upwards of like 5 or 6 dimensions for a particular tensor. And the reason why we use torch tensors is it keeps track of the relationships between this tensor and this tensor. So if this tensor is a derived quantity of this tensor, it'll keep track of those relationships. So when it needs to calculate derivatives of tensors with respect to tensors, it knows how to do those things. So we just cast those NumPy arrays as float tensors, and then we'll print out the shape of what these guys are. So let's start out doing that. You can see all we did was pass in a NumPy vector of 1 by 1,000, and our torch tensor is 1 by 1,000. So the next thing that we want to do is pass that through our linear layer. And then we'll look at what the output shape of that is. Does anybody know what the output shape of our linear layer should be? Not all at once, guys. Not all at once. Oh, yeah. Yeah, so for folks that joined late, if you want to get the code for what we're walking through now, you can go to Zachary S. Brown Deep Learning NLP SAIS. And you can just download the code from there. Leave this up for one more second. So does anybody know what the shape of the output from our linear layer is? We just passed in a vector of length 1,000. And do you remember when I defined the linear layer, what was the output shape that I had for that? 1, yeah. So what this linear layer is going to do, the linear layer is just a vector of weights, and I'm passing in a vector. We're just going to take the dot product of those things, which produces a scalar, just a length 1, length 1 value. Now, if our linear layer was 2 by whatever our input dimension was, then we would have a 2-dimensional output. We would have 2 different distinct values there. We would still be taking the dot product between different parts, between our vector and our matrices. Our vector and the columns in our matrix, so we would get 2 different distinct values there. So if I run this guy, we see that the shape of the linear output is indeed just 1 by 1. Now what we want to do is squish that guy down. So after we after we take our linear output, that thing is unbounded. It can be between -infinity and infinity, depending on what our weights are and what our input values are. And we want to be able to interpret this thing as a probability. So we use a sigmoid function and we just squish that guy down. So you can see we are indeed squishing that down to some value in between 0 and 1, and we haven't trained our model at all, and it's good that this is falling like roughly between. Our model isn't saying that for this particular input vector it should be negative sentiment or it should be positive sentiment. It's like, I don't know what it is. So now let's actually do one set of backprops. So the first thing that we want to do is calculate our loss. So I'll take that sigmoid output, and I'm just going to reshape it using this dot view to the right shape for the binary cross entropy input. And I'll pass in that, and I'll just pass in whatever the true value is here. Then we can get what the value for the actual loss is. So we were off by this much as measured by binary cross entropy. So cool, that doesn't mean anything to me, but we can use that to update what all of our weights are. So we can calculate these gradients, and then we can update what all of our weights are. So in order to calculate the gradients, we just take that loss and we call the dot backward method on it. So what that backward does is loss has an internal graph of all of the different variable dependencies that went into calculating it. So when you call backward, it just calculates the gradient of every single variable that went into the calculation of that with respect to, it calculates the gradient of the loss with respect to every variable that went into it. So when we call this backward thing, we should be able to see for these linear parameters an actual gradient value attached to them. So we'll call loss.backward, and then we'll print out what our bias value is. That's just one of the weights, and then we'll see that it actually has a gradient attached to it now. So we have our actual value for the bias. Our current value is 0.01. And then we have this gradient that's been calculated when we called loss.backwards. And we're going to use this thing along with our learning rate to update the value of that particular weight. So we do that by just calling optim.step. So remember, optim was our stochastic gradient descent optimizer. And we're just going to take one step in our optimizer. And that just means take our current weights, subtract off the gradient of that weight with respect to the loss function times the learning rate, and then update those guys. So we can do all of that. And you can see that the bias actually changes value. The bias gradient was this. It's different because we ran it again. And yeah, so all this is just showing you that there isn't any like voodoo magic or anything going on under the hood with deep learning and with stochastic gradient descent and backpropagation and all of that fun stuff. And if you're learning this stuff for the first time and you're putting together you're like, I know that this model works like this, you can literally just define all of the different pieces that go into a model and then send your data through them one bit at a time and make sure that everything that you think is going on is actually going on. And for me, this is a hugely invaluable learning tool. So we can look at what the actual linear output are and what the actual sigmoid output is. So you can see that this linear output was a negative value, and now we've squished it down to be a non-negative 0,1 bounded value. So cool. So now we've shown what all of these different things are, but we've only passed one particular training example through our perceptron, and that's not useful. With machine learning, we usually pass all of our training examples through our particular model. So let's look at how we would actually train this thing. So I'm going to set some variable called total loss, and I'm just going to update this with what the total loss is as we're running through. And then I'm just going to loop through all of the examples in my train data. I'm going to zero out my gradients. So what that means is after every time I pass data through, that's going to accumulate gradients on my optimizer, and I don't want those things to just add up over time. You have to reset them back to 0 every time you run a pass forward. Then I'm going to take a single example, take the features and the truth, cast those as float tensors just like I did before, pass them through the linear layer, through the sigmoid, calculate my loss, and add to my total loss, call loss.backwards, call optim.step. Notice I'm calling loss.data.numpy here. This is just so I don't accumulate a tensor value. This is just getting to the data that underlies that tensor value. So this won't take too long to train because it's a really, really, really simple model, and it doesn't have a ton of parameters in it. So cool, so we trained a model. Now how does this actually do? So you remember before I held out some training data. I used train test split, and I had some train data and some test data. So we ran through 75% of the data that we had to train, and now let's evaluate that on our actual test data. So the only thing that we need to do for that is to take all of our test data, cast it as float tensors again, run it through our linear layer, our trained linear layer, run it through our sigmoid, and then I'm just going to append that value to an array that I'm going to call yTrue, and append the predicted value here as well. And then I'm just going to pick some random threshold of 0.5 and calculate what my accuracy is for this. So I'm going to say that everything with a probability over 0.5, I'm going to say that's true, and everything else I'm going to call false. So we get a validation accuracy of 0.8. That's not great, but this took like 30 seconds to train on our computer, and we're using the absolute simplest approach in the world. So that's not bad either for us just trying something. Also, can any of the data scientists in the room tell me, based on our distribution of class labels, is this good or bad? It's decent, right? Like if we had a distribution of data labels that was 80%, 20%, then this is probably really bad. But we have a 50-50 split for our labels, so we're actually getting some lift here. So this whole process that I walked through here, where I'm training my model and I'm explicitly calling a linear layer and then a sigmoid layer and all of this stuff, this isn't really typical, and this isn't what you would see in the PyTorch documentation. If you go to the PyTorch documentation, they have everything defined like they have the linear module defined here. So you can actually do that. So I have a modules directory here, and I have something called Perceptron, and I'm just going to import that particular class from in there. So let's just take a look at that really quickly. Can folks see this in the back? Yeah? Cool. So I've just imported all of the other things that I was using before, and then I'm just going to subclass the torch.nn.module, and this right here is boilerplate. This looked scary to me the first time I looked at it and wrote it, but this is just something that you get super used to writing. So you superclass whatever your class is called, and call the init of torch.nn.module, and then you continue along with your init. So the only things that you have to have for a torch module are an init function, which just tells you all the things to set up for your particular module. In this case, we're just defining as an attribute of our perceptron, we're just having a linear and a sigmoid, and then a forward pass. So this just defines exactly what you want to happen to your data using all of the attributes of using all the submodules of your overall module. So here we're just passing it through our linear layer, passing it through our sigmoid, and then just returning that value. So in this instance, it doesn't save us a whole bunch of screen space, But for really complex models where you have a whole bunch of like 10 linear layers and an RNN and convolutional neural nets and all of that stuff, it really helps out a lot if you can modularize all of the different parts that you're passing data around through. So here also, I'm going to not just run through my data once, but I'll run through my data 5 times, and I'm going to run through 5 different epochs. So here I just define my model. It's a perceptron, and the only input parameter that I have for my perceptron on initialization is just what is my input shape? What's the length of my vector that I'm going to be passing into this thing? So that's max features, same thing that it was before, 1,000. Specify my criterion, my loss function, and the optimizer, and then loop through 5 epochs. Call model.train. All model.train does is just turn off any sort of like random dropout-like element. So if you have some, if you're using a regularization scheme like dropout, model.train just turns off the dropout for, turns on the dropout for that particular pass. Specify my total loss, and then just loop through all of my data again here. And see, instead of actually passing my data by hand through the linear layer and through the sigmoid, now I'm just calling model.forward with all of my data. So we can just train this guy, and this will train for 5 epochs, and we should see that as I pass through all of my data multiple times, we should see the accuracy increase and the overall loss decrease. Now, can anybody tell me why, if we're just passing through the same data over and over again, why we would still be having increased accuracy? For a lot of machine learning models that you get out of scikit-learn or something, you typically just pass your data through once. You don't keep training your model, and that's not really the case with deep learning. So does anybody know why? I got that question the first time I gave this talk, and I thought it was an interesting one. Pardon? Yeah. So we're updating our weights based on our loss function, and the way that I like to think about it is we have this high-dimensional space of all of our parameters that go into our model, and we just start out somewhere randomly in that parameter space. So every time we loop through our data, every time we update each one of those parameters, we're just taking a step in that parameter space. But when you first start out maybe here in the parameter space, and then after you've gone through all of your data once, you're maybe over here now. So that data might still have useful information about how to explore this other area of the parameter space and how to further optimize on your data set. So that's why you typically pass through multiple epochs for a deep learning process. So you can see our loss was decreasing here. It was still continuing to decrease, although it looks like it was slowing down a little bit. And we got our validation accuracy to go up by 4%. So this isn't that bad. I mean, not that bad at all, considering it would have taken like, I don't know, 15, 20 minutes to code this up. So now let's move forward a little bit and go to how do we take this particular binary document classification, which is essentially what we just did. We took some text, vectorized it, and created a binary output. How do we move from that to multi-class document classification? These two, the way that I've framed these two, they look really, really similar. Everything to the left of here, or to the left of the task, is really the same, and the output shape is the only thing that we're changing. And that's why I really, really like deep learning, especially for natural language processing problems, is just because of how modular everything is. If I want to switch over to a multi-class classification, all I have to do is make one major change to my module. And that's, instead of my linear layer, remember before we specified that the output shape of that thing was just 1. If I have a 3-class classifier, I just specify the output shape of that to be 3. And then I'm not going to use a sigmoid anymore, because a sigmoid is good for squishing down one number, and I want to normalize the probability over all of those different classes. So I'll use the multidimensional analog of the sigmoid, which is a softmax function, but that just distributes the weights across an entire vector. So here we'll actually just train a similar model. I've pulled from, I think it's Google or something, has this whole repository of Stack Overflow questions and answers. And I've pulled the text for the actual title of a whole bunch of these questions, and then just what the tag was. So whether it was in, I think that I have 8 different tags here, so 8 potential output classes. So was this tagged with JavaScript or Android or Java or Python or something like that? So what I want to do is see if based on the text, based on the title of whatever the Stack Overflow question was, can I predict what the label is? So can I learn relationships between particular, like questions that would be asked about particular languages and whether or not that was the language? So again, I have clean text. I'm doing all of the stuff that I did before. Here, I'm limiting to max features of 1,000. So here, this corpus is much smaller because before they were movie reviews. Now they're just shorter strings. They're much shorter strings that are just the title of a particular Stack Overflow question. So now I'm going to create a linear layer, but instead of but instead of having an output size of 1, I'm just going to have an output size of whatever label size is. So let's see what label sizes here. Yeah, so we have five different classes. So then I'm going to use a softmax normalization. So instead of my sigmoid, I'm just replacing that with softmax. I'm using log softmax because it's more numerically stable in the optimization, but it's roughly the same thing. And then this is the loss function that goes along with the log softmax, so negative log likelihood loss. And then we're going to use the same exact optimizer. So we'll run that guy. And then we can see that our input tensor shape was 1 by 1,000. Our this is our label tensor shape. Our linear output shape is 1 by 5. Our softmax output shape is 1 by 5 as well. We wouldn't expect that to change the shape. And our softmax normalization, we want to make sure that we're actually summing all of these guys up to 1. A normalized probability sums up to 1, and in which case this does. And then this is our overall loss value. So we're doing the same exact thing that we did before. The only thing that we've really changed here fundamentally about our model is just that we're changing our output dimension of our linear layer to be 5 instead of 1. So we have a multi-class perceptron here, and again, we've changed our softmax, this from a sigmoid to a softmax. But we really haven't changed much else at all in this layer at all, except the fact that we have an output shape of 5 here, or a settable output shape. So we can run this guy, and I'm actually going to change this to not run for 10 epochs, because this will take a little bit. We'll run it for 3, and we should again see the validation accuracy going up as we run through our data set more and more. So I'll actually pause here and take a couple sips of my coffee and catch my breath, and answer any questions if folks have any questions on this stuff, just the basics of neural nets. Any at all?
Got a question.
Mm-hmm.
Yeah, right here. So you're saying that we are exploring the space for the different weights, right? So we're going from this point to that point, but just changing the weight or a particular weight a little bit. And maybe once you get to this other location in the space, then you are going to tweak another one maybe, and then go to a different place. But my question is there any way we can control the way we are doing that exploration in the space?
So the question is, as we're exploring a parameter space using stochastic gradient descent, is there any way that we can actually explore the direction that we're going along there? So the control of the direction that we're using is the fact that we're going in the direction of the gradient. So we're essentially, it's a steepest descent algorithm. So it's saying in this high dimensional space, what's the direction that goes downhill the fastest? And I'm just going to take a step in that direction. So in some sense, we are controlling it by going in the direction of the gradient. There are a whole bunch of different types of algorithms that have, like, for example, a memory of like your last 3 steps. So they'll keep track of, they'll try to keep you going along roughly the same direction and not take like some 90-degree turn just because one particular update said go this way instead. So there's a whole bunch of different algorithms that will that keep a little bit more information. But yeah, that's I guess that would be my answer. Is if you want to include more information, then just try a different descent algorithm. Cool. Any other questions? Looks like this is done running. I'll take one. Yep.
Yeah, so you said that you like PyTorch because you control each step and like exactly what you're doing now. But I was thinking, this you would be doing it in batches, right, of data.
Mm-hmm.
Where is that specified? Is it within, is it something you want to control?
Yes. Yeah, so the question is, for all of these examples, I've been highlighting the fact that I really like PyTorch because you control all the things. And she's bringing up the fact that I haven't specified batches anywhere. So usually when you run things for deep learning calculations, you don't just run a single example through at a time, but a lot of times you're running, you're parallelizing your linear algebra across a GPU. So you'll run a whole bunch of examples at the same time, which would be known as batching. Here I'm brushing that all under the carpet and just ignoring batching overall. But yeah. So that would just you would just specify an additional batch dimension for all of your tensors, and then that can be whatever you want. So it's just you give your tensors another dimension, or in this case, I think that my batch dimension is, if you remember, the dimension of my input vector was 1 by 1,000. That first dimension is the batch dimension. So I have a batch size of 1 here.
Can you do shuffling also?
Yeah, so you can. By default, you would just do it by hand, but there are a whole bunch of different data loaders built into Torch that will handle shuffling and all of that stuff for you. It also, to some extent, handle memory management and not require that you have everything loaded into memory to send it through, but you can read things on the fly from disk and run them through your model, so you don't have to hold your whole data set in memory at once. So there's, I think, torch.data.utils. There's a class called data loader, which you can superclass and get all of that fun functionality.
So does it have similar API as TensorFlow data APIs?
I would imagine so, but I haven't played around with TensorFlow enough to be able to definitively say. Cool, I can take one more question before we get back to this. Yep. The derivative itself isn't always negative, but you're always subtracting off, yeah. Because you want to move downhill instead of uphill. If you write out the math, it does, like you're subtracting off the gradient, so that moves you in the direction of descent as opposed to ascent. Yeah. Cool. So that is a basic perceptron. Now let me go back to.
Can you just
Open the GitHub link again? Sure. Mm-hmm. Oh, and one thing that I will say that I forgot to call out, in each one of the notebooks that I'm going to walk through, in the GitHub repo, I have the same notebook name, but with -stub next to it. And what that has is, for that particular cell that I just walked through that shows like passing the data through each one of the elements of whatever model we're putting together, it doesn't have any of that code filled out. So if you just want to build a little bit of muscle memory for figuring out like how do I pass these different shaped objects through and make sure that I'm getting the right shape out, you can look at the stub and just play along at home. Mm-hmm.
Instead of the STD optimizer, Adam would be, is it performing better?
It depends on your task. So Adam is, for this, I don't know. I mean, it's like a simple enough problem to where I'm not sure that you'd get much lift with Adam. I've actually found for certain tasks, if you look in the academic literature, some of the tasks that I've worked on, specifically around like named entity recognition, go against the grain, and in some of the papers it'll say like our best performance was found with a batch size of 1 and stochastic gradient descent. So it really depends on your data set and the particular problem. So now I'll jump into looking at sequential models. So let me jump back into my slides. So now we're going to talk about vectorization and classification with recurrent neural networks. So I'll go through a little bit of how we would encode text with a recurrent neural network and what recurrent neural networks are, and then I'll talk a little bit about word embeddings, just touch on those briefly, and then we'll walk into another example of how we would actually do this in PyTorch. So we just walked through an example of multi-class document classification, and for our vectorization, we used TF-IDF vectorization. Now we're still going to use our same perceptron classifier that we just used, but instead of using a TF-IDF vectorization, which was necessarily lossy, we hacked off a huge area of our corpus, we're going to use a recurrent neural net to create a vector from our sequence of text. So what is a recurrent neural net? A recurrent neural net looks a lot like the perceptron that we just had, and also just a quick call out to Christopher Ola. I've taken all of these pictures from there just because they're the prettiest pictures that I could find, and I can't make pictures this pretty. There's that, and a recurrent neural net just takes in an input vector. So you can think of this being the same diagram that I had for our perceptron, but just instead of our input data being fed in from the left, now it's being fed in from the bottom. So this x of t represents our whole vector of input. This A represents whatever weights that we have for our particular model, and then we output some sort of, he uses h of t here for our hypothesis, but this is just the output. So this is an input vector, and this is an output vector, just like we had for our perceptron. You'll notice the only difference here is that we have this line that loops around and feeds back into itself. So if we unroll this thing, what that really means is if we have a sequence of input vectors, so a whole bunch of different input vectors, let's say that represent words or something, we can feed these into our neural net and output a vector for that particular input, and we also pass that to the right, back into the same exact network. So now the network has an idea of both the new vector that you're passing in, the new data, as well as what the network has already seen from our previous data. So you pass in a sequence, and then each output element, as you move along this sequence, has some knowledge of the input elements that came before it. So a vanilla recurrent neural network just has a very simple combination here. You just run it through a hyperbolic tangent activation function as opposed to a sigmoid, and then output your hypothesis here, and you actually pass that same hypothesis vector to the right. Kind of the hotness, maybe, I guess it's a couple years ago now, were long short-term memory networks, which just do more complicated stuff in here. The only difference that I'll call out is instead of for a vanilla recurrent neural network where you just pass a single vector to the right, these long short-term memory networks pass two vectors to the right, and they do that so they can try to keep a longer memory of the entire sequence. So vanilla recurrent neural networks were a pretty cool development, but they had this I guess, feature where they would forget after, let's say, maybe 10 steps in your sequence or even shorter. So long short-term memory networks were just a way to try to pass, use a gate to pass more information forward from further back. So the only thing that I'm going to ask you to remember from this complicated diagram is just that we have a vector go in, a single vector go out, and then we pass two things to the right every time we send a vector through. So if we pass a whole sequence of this stuff through, we would expect if we pass a sequence of vectors in, that we would get a sequence of vectors out. And this vector down here would have some sort of contextual knowledge of all of these input vectors down here. So this is what we would call a contextualized representation of this input sequence. It has some knowledge of the entire input sequence. So when things like word orderings are important, then you want to use some sort of a contextualized representation like this. So we're going to encode a sequence into a single vector. So although our recurrent neural network is going to output an output vector for every input vector that we send in, we're actually only going to use this last one. So if we want to take an entire sequence of things and encode it into a single vector, because this is a contextualized representation of all of the inputs, we can just take that last one. And if we want to classify that sequence, we can just slap up something like a perceptron on the end of that, because we know that this works for classification for some arbitrary vector. So instead, before this h of t was being produced with TF-IDF vectorization, now this h of t is being produced using a contextualized representation produced out of a recurrent neural network. So this can be used for sequence classification. If we just take a whole bunch of words, the quick brown fox jumped over the fence, and we want to get the sentiment of that, that produces an h of t here, some sort of a vector representation, contextualized vector representation of this whole sentence, and then we pass that vectorized representation into our softmax. But what about the inputs to this RNN? Like before I was saying the cool thing about, like I just kind of used a count-based approach, TF-IDF vectorization, to get vector representations of each one of our words and also of our documents. Excuse me. So how do we actually, right here I'm passing in words. I can't just feed words directly to my neural net. So what I'll actually do is just use word embeddings that were trained from, I think that I'm loading in glove vectors for this particular example. So I'm not going to get into how word embeddings are calculated. That's a pretty deep subject these days. But I will touch briefly on how word embeddings are different from a bag of words or a count-based vector representation. So if we think of a typical count-based vector representation, we're treating every word in a document as a different direction in some high-dimensional vector space. So each one of those words represents an orthogonal direction in some really, really high-dimensional vector space. Now the problem with this, well, there are a couple problems with this. One of them is that as you get to larger and larger corpora of text, this vector space gets really, really highly dimensional. Some of the things that we deal with at work where we use these bag of words approaches go up to like maybe 200,000 dimensions or something. If you're using an efficient classification algorithm downstream, it doesn't really matter. But the other thing that you're lacking is that because all of these vectors are orthogonal to each other, this representation captures absolutely no information about relationships between each one of these words. And all of these words have semantic relationships between them that we would be able to understand. So like I said, I won't go into the details, but there are a lot of algorithms out these days, unsupervised algorithms, that will create a dense representation of your word vector space such that words that are more semantically similar are closer in that vector space than words that are not semantically similar. Which is a really, really useful feature, especially to be training models on, because if your words already have, if your input vectors to a model already have some understanding of semantic similarity, then you're already going to get a little bit of a boost just by having those pre-trained word embeddings. So this is a simple way of something along the lines of transfer learning for natural language processing tasks. So if you want to learn anything more about word embeddings, please talk to me afterwards. I also have a talk, I think on SlideShare or something, that goes more into depth on word embeddings and some of the state-of-the-art approaches that are out there. So now that we've talked about encoding a sequence of words with a recurrent neural network, let's see what this actually looks like in code. So here again, I'm going to just import a whole bunch of necessary things, train test split, accuracy score, and here I'm going to import a linear layer, something called an embedding layer, something, an RNN, a GRU, and an LSTM, which are all essentially just recurrent neural networks. They all will pass something to the right and emit some sort of an output. For this, I'm using the Reuters 8 data set. So this has a whole bunch of news articles from like the mid-90s, I think, and hand-annotated tags of what type of information was contained in this news article. So it's called R8 because there are 8 different categories, and we can see what they look like. Oops, I didn't execute my cells. So you can see like earnings, acquisitions, earnings. There are 8 different categories here. And all I'm doing is the same normalization that I was doing before with cleaning up my text. So I'm actually not going to use pre-trained embeddings for this particular example. So I'm not going to say, okay, I had some other model that figured these things out. What I'm going to do is, if I go back to here, you could represent this thing as just a lookup of a vector for a particular word. So what if I just created some lookup of a vector for a particular word for all the words in my corpus, but instead of having an actual vector here, that's the thing that I want to figure out, right? So what if I just took all of these guys and just initialized them with weights that can then be learned with stochastic gradient descent as well? This is what an embedding layer does. An embedding layer is just a lookup that takes in an index that represents a particular word and maps a vector of weights to that index, and then you just use backpropagation and stochastic gradient descent to just learn what those weights are as well. Just a disclaimer, this adds a lot of additional weights to your model. It adds, so you can specify whatever you want this vector dimension to be. So let's say that we had 1,000 words in our corpus and we had of an embedding dimension of 10, then that's adding 10,000 additional weights into your model. So just be cognizant of that if you try to learn your own embeddings as you're going along. Another comment on that is if you do learn your own embeddings for a particular task, in a lot of cases it can be useful because we work with financial data a lot at S&P, and we tend to just try out glove embeddings or something first, or word-to-vec embeddings. And because we have such a specialized content domain, domain for our corpus, sometimes the word embeddings that are just off the shelf, publicly available, they don't do the best job on our particular domain. So you can either just learn your own embeddings like this, train your own word-to-vec model or something, or just load in pre-trained embeddings and then allow those embeddings to be updated. So that kind of gives you a starting space in your optimization. Cool, so that is my little spiel on embeddings. In order to actually get at the things that we'll need for one of these embeddings, we have to know how many words we have. We need to basically know how many elements in that lookup we have. And then we also have to convert the individual words into just numeric indices, so we don't have to, so PyTorch doesn't have to deal with characters at all. So what I'm going to do here is just split all of my data, all of my cleaned data, and then this little itertools function that's like all over my code these days just figures out the unique set of all of the words that we have. One more comment on this. PyTorch has stuff that does all of these things that I'm doing here. I just wanted to spell it out in all the gory detail just so it's very apparent what's going on. I don't like in tutorials when there's a lot of functions that just do all of this stuff for you. But PyTorch does have things that, utilities that will do all of this stuff. Then I'm just gonna say my vocab size is the length of all of my distinct words there. So then I wanna learn weights, vector representations of all of these different words. I'll do the same thing for all of my labels because I don't want it. This is essentially integer encoding all of my labels. And then I'll create a lookup word to index, which just gives me for every word that I have what numeric index I'm assigning to it, and then index to word, which is just the reverse. Same thing for label, and then I'll create a new data frame with the text encoded as just a sequence of integers. So instead of a sequence of words, now I just have a list that contains a sequence of integers, and the same thing for my labels as well. So we can look at, somebody's got to go if their alarm's going off. Let's look at let's look at data.head. just to make it a little bit more apparent. Yes, you can see here we have our text cleaned as just a space-delimited sequence of words. And here all I've done is just translated those into whatever integers I want to represent those words. And that is going to be the input to my model, just this sequence, this list of integers. Yep, go ahead.
So I see the word brown there, right? So if you have the color brown, like someone's name is brown, if you lowercase it, the vectors will be the same. So how do you deal with cases like that where like capitals, like, because you have US with us, but then capital US is like America, right?
Yeah.
How do you deal with cases like that?
It depends on your particular problem. So if you expect to have that happening a lot, like if specific names are going to be really, really important, then you can maybe learn a different embedding for capital Brown versus lowercase brown. And in a lot of the pre-trained corpora, it will actually either say cased or uncased. So you can usually download like Word2Vec with both done, depending on your use case. But yeah, I hate to say it depends, but it depends. Another thing that you can do with that, though, is if something is, let's say you're reading through a sentence and it said the cow is brown and the presenter's name is Zachary Brown. If we cased that whole thing and converted it all to lowercase, if you run that through an LSTM or some sort of a recurrent neural network, the output for each one of the input vectors that you're sending through, even though the input vector might be the same for brown because you've cased it, the output vector from sending it through a sequential model will be a contextualized representation of that. So that should capture the fact that this thing that came before this brown looks a lot more like a name or something, and the thing that came before this brown looked a lot more like an animal or something. So that's what's nice about these sequential models, is they allow you to create contextualized representations, even if you're starting from a more generalized corpus. Mm-hmm.
So repetitive text. So we have to actually repeat it, or it's only one index?
Wait, I'm sorry, say that one more time.
Champion, right? So
Mm-hmm.
champion and any other row, the index is the same for champion.
Yes. Yeah, so the question is this a unique index for the word champion? And yeah. So I've done that by just getting a unique set of all the words and then looping through them and just manually doing the indexing. So cool, so this is what we're starting with. We're starting with just sequences of integers, and now we're going to define all the pieces that we need to run create embeddings for all of these indexes that we have, that we will learn, and then run those through an LSTM and create a single vector output from that LSTM, just grabbing the last the last output state from that, and then taking that and running it through a perceptron. So for that, we're going to need an embedding layer, and all you need to initialize in an embedding layer is just the number of embeddings that you want. In this case, it's just the number of unique words that we had in our corpus, and then how big we want our embedding dimension to be. This is probably way overkill for this problem, but I can train it. Then we initialize an LSTM. I specify my input size, which is the shape of the vector that's coming in from the bottom. And then I specify my hidden size, which is going to be the shape of a few different things. So the hidden size is going to be the shape of this vector and the shape of these vectors. See, this vector is the same as this vector down here, so these two are by default the same shape, and then it's also going to be the shape of this vector. So when we first start out with our LSTM, we actually have to initialize both of these guys. So you'll see that I initialize two vectors of zeros down below that we pass in as the initial hidden states of this guy. Mm-hmm. This guy? This is just, so in this case, we just have 1 and all zeros. In this case, this is just our embedding dimension. So we can just specify whatever dimension we want to compute embeddings for. So we specify what this dimension is, and these columns don't really have any meaning in and of themselves. So it's not like it has this much of this thing and that much of that thing. But the relationships, the spatial relationships between entities in that vector space are what's important. Good question. Mm-hmm.
When you initialize
The LSTM what?
How many cells you want?
Yes, yeah. So the question is, when we initialize our LSTM layer, is there a way to specify how many LSTM cells we are or we want? And yes, I haven't done that there. I'm assuming that it's just a single cell LSTM, but you can actually stack LSTMs on top of each other and just pass your data up and over. And what that'll do is it'll create higher level representations of each one of your input vectors, and it will also allow different paths for the data to travel along, so you can capture more complex syntactical relationships. But I'm glossing over that for the time being. So to go back down to the things that we need, so we need our vocabulary size for our embedding layer, and then the dimension of our embedding layer. So we're going to capture or create 100 dimensional vectors for each one of our words, and we're just going to learn those as weights. For our LSTM, we just specify our input size. In this case, it's 100 because we're creating 100 dimensional representations of our words. And then our hidden size is going to be 50. So that means that the output vectors from our LSTM are going to be 50 dimensional vectors. Here, I'm initializing the 2 vector hidden states. So both of those are going to be of dimension 50. And then one of these is the batch size, and the other one, I forget what it is, so I'm sorry. Then I concatenate those guys into a tuple, and that's going to be my initial hidden state, so just zeros. And then after I pass my sequence through my LSTM, I want to use something like a perceptron to classify that. So I'll just add one more linear layer that will take the output shape of my LSTM. So my LSTM is going to output vectors of shape 50, and then my label size. So this is basically going to say, okay, I have this 50-dimensional representation of my whole sentence, and then I want to collapse that down into how many labels I have. Then I'll toss a softmax on top of that to give me a probability distribution, and then the same negative log likelihood loss. Yep. How did I decide the size of the embedding? Yeah, 100 looked like a nice round number for the, so in practice, I'll usually choose an embedding size based on how large my corpus is and how complex the language in my corpus is. So if you have a really, really large corpus with tons of complex language, maybe you'll want to go up to something like 300. For very small corpora, maybe you can get away with something like 100 or 50 or 64, something like that. You can also do the same thing with character embeddings and create character level models where your token is not a word, but it's a character. For a lot of character level models, they'll use embedding sizes of like 50, and that's for like, I don't know, a couple hundred different characters that you could have. So a lot of times I just go by whatever the literature is using for the particular model type or whatever they found best. The thing about running a lot of these algorithms on your own computer, especially if you're trying to do stuff from scratch, is you usually don't have the computational resources that somebody like Google or a heavy hitter like that's going to have. But you can a lot of times just take all of the learning that they've done by exploring that parameter space in their papers, and they'll say like, this didn't work well, this didn't work well, so we chose this, and you can go with their choices. Mm-hmm. Yeah. Yeah. So yeah, her comment was about domain specificity. So you might have the choice for your embedding dimension might very heavily depend on how domain specific your corpus is as well. I think I saw another question back here. Yep.
For non-Latin language like Japanese, like kanji, do you consider a kanji character as one letter to avoid that kind of technique?
that opens up a whole can of worms. You can use a whole bunch of different techniques to do that. You could treat sequences of them as a single token, if you will, or a single kanji letter as a token. And it would probably just depend on your modeling task, whatever your downstream task that you're trying to do is, and your understanding of the language.
So you initialize the zeros, like second one, is that a channel that you're specifying?
This guy?
Yeah, second one.
The second one. Yeah, I'd have to look in the. So I'm having a blank right now. I'm drawing a blank. It is, yeah, so it is your number of stacks that you have. Yeah, so you'd have to specify 2 of these guys if you had a stacked LSTM. Yeah, good point. Cool, and then we're going to do the same thing that we did before, just walking through each one of the steps, running our data through each one of these different layer types. So the first thing that we're going to do is just grab our features and our labels, and then convert those to, in this case, we're going to convert them to long tensors because I've integer encoded everything, so that's what they expect. And we can just look at what our shapes for different things are now. So our feature sequence shape is 62 words long, and our target shape is just 1. We just have a single output for this thing that's been integer encoded. Now I'm going to pass this through my embedding layer. So I had a sequence that was 62 words long. So can anybody tell me what the embedding sequence shape should be? Yeah, 62 by 100. So we're taking all of those integers, and then we're replacing all of those integers with just the vector representation, which at this point we haven't learned what any of those weights are, so they're just going to have been initialized with random small, I believe, Gaussian distributed weights. So you can see, oh no, name embedding is not defined. I forgot to run my imports again, guys. Oh, I didn't run the one above, did I? There we go. Yep, so 62 by 100. So now we have you can think of this as just a matrix, right? But each one of those 62 elements in the matrix is just a vector of length 100, and then we're going to pass that whole thing through our LSTM. And so we just printed out what our embedding shape is. Now I'm going to unsqueeze that guy, which means I'm going to add an additional dimension for my batch size, because LSTM's just, the implementation in PyTorch requires that you pass in something with a batch size, so I'm going to give it an additional dimension with the batch size. And then we're going to just pass that through. So the way that you pass something through an LSTM is you call your LSTM, you pass in whatever sequence you want to, and then you pass in what the hidden state is. Our hidden state I had initialized to those zeros, and our embedded sequence is just that 62 by 100 sequence, and then it returns the hidden state and also the output. So let's see what the output shape is. So our output shape is 62 by 50. So what we've done is for every input, we've produced some new output, and then we have 62 of these guys. And now instead of being 100 dimensional, now they're 50 dimensional. So these are the hidden states, and these are contextualized representations of each one of those input words. So now if we want a contextualized representation of the overall sentence, we can just take the last one of these guys. The last one of these should have information encoded in it from all of the previous words that went through the model. So see here, I'm taking the final output, which is your LSTM output, and the last element of that. And then this should be the input to my linear layer. So here I'm just going to, for my linear layer, just pass in a vector of shape 1 by 50. And then everything proceeds just like it did for our perceptron. So we're going to print our linear output shape, which should just be the number of classes. So this is the R8 data set, so it has 8 different classes. And run it through our softmax activation. This should not change the shape, because this is just a normalization for that output vector to make it look more like a probability. And then we can again print out our loss. So all that stuff is fun. So what we've done here is just run it through each one of the steps for this somewhat complex model and just verify that the shapes are exactly the stuff that I've talked about above. And this isn't so important when you're running through a model that's pretty straightforward like this, but it gets a lot more important when you're creating really, really complex models and you're modularizing all of these different parts, and you know that this module takes in this shape and produces this shape. You can just modularize all of these different things and then just pass data around from module to module and piece these things together like they're Legos, and it's a lot of fun. So here I'm going to just import a module that will do this. So I have a classification module here. So let's look at this guy. So we have an RNN classifier, and I'm setting our vocab size, our embedding dimension, our hidden dimension, our output dimension, and our batch size. All of these things when I initialize it. So our vocab size, remember this and our embedding dim are used for our embedding layer. Our linear layer takes that hidden dim, which is the output size for your linear layer, and the output dimension, so that's how many classes you have. Batch size I'm just setting because you need it for your LSTMs. And then for our forward, you just pass it through your embedding, reshape it just a little bit so it's prettier for the RNN, run it through your RNN, grab the last element of your RNN, run a softmax over that, and then just return your softmax output. I also have an additional convenience function down here to just initialize all of my hidden states with zeros. So this is exactly what we saw before. And I'm going to import that model. Yep. I think so, yeah.
So you covered it briefly before, but not to go through the whole code again. I was wondering, so the embedding, you said it gets updated with gradient descent as well.
Mm-hmm.
But how does that actually function? I mean, which error is propagated back to change those?
So it's the same, you do it the exact same way that you update the weights for your linear layer, except that these are just like some downstream, let me think. So you calculate the derivative with respect to that weight, and you use that using the chain rule of calculus. So it's the derivative with respect to this function, you just keep. Yes, yeah, just like it's another hidden layer, except it's really, really simple because it's just all of those weights are just like a dictionary lookup. So it's pretty straightforward to. So there are a lot more complex functional dependencies depending on like how you're sending, how you're combining different weight vectors, and an embedding layer is a pretty simple one. Any other questions? Mm-hmm. Where does the learning happen for the embedding? It happens the same time when you call backward on your. It happens just with gradient descent, just like when you're training your actual model. So I am passing a label, though. You're not passing a label for each one of your words necessarily, but you're passing in a label for the downstream task, and it will learn optimal weights for your words that help contribute to that task. Yes, yep, so you backpropagate through the whole thing. And that's where things get really, really cool, because you can, a lot of people will take a deep learning model and combine the output from your deep learning model into a traditional machine learning classifier. And what you're missing out on there is if you just implement your traditional machine learning classifier in PyTorch as a module, then you can backprop through the whole thing and learn the whole problem end to end. So you're not like creating an information bottleneck. Good question. So here I'm creating an RNN classifier object, specifying all of those things, specifying my optimization and criteria, my loss function here, running through 10 epochs and doing all of the things that I did before. For my prediction, I'm using torch.argmax, which just takes whatever, I have a softmax output, so this just takes the thing with the highest probability and calls that my prediction. And I'm keeping track for my test data, which was the actual prediction. Here, I'm only using the first 32 elements of the sequence because this takes quite a while to train if you don't, because there are some sequences that are really, really long, and LSTMs are notoriously slow to train if you have really long sequences. But we can actually start this guy training. And this will take, I think, a couple minutes, so I can take a couple more questions while we're at it. How are we doing on time? Looks like we have a few more minutes, so we'll probably just get through the rest of this module, and then maybe call it quits. Yep. Yeah, so that's a really good question. So the question is, if we have a set of these features that we've gotten from the text using something like an LSTM or any sort of text vectorization process, and then we have this other set of features that we've hand engineered maybe, or they're contextual to whatever text that you're trying to classify. How do we combine those two things? And the answer is there's a lot of different ways that you can do it. One way that I've seen work in the past is to take your contextualized representation, maybe using a bidirectional LSTM, so you're going both ways through your data. So that gives you one vector. And then you have another vector of, let's say, one hot encoded features or something like that, anything like that. You can take those guys and concatenate them. The thing that you need to be careful of is making sure that the normalization of both of them is right. So you might want to L2 norm both of them to make sure that one isn't being overweighted relative to the other one. You'll see stuff like that happen a lot in different models, though. Usually they do that in this, near the end of the whole process. So you'll do all of your text stuff, and then you'll pass in this context vector, you might want to call it, and concatenate those, L2 norm them, concatenate them, and then maybe pass them through one additional linear layer so they can have some mixing in that linear layer, and then have your final classification after that. So I would say that I've seen it happen the most near the end, but they usually do allow one more layer, at least for some sort of interaction between the two. Cool. So here you can see that this is training. I talked a bit slower. I think this session is done at 3:20. Is that right? Yeah? Can anybody confirm that? Can we get a thumbs up? Yeah, it's done at 3:20, cool. So what I'm going to point out are the high-level things from the next notebook that I have. So the next notebook is going on to part of speech tagging. And the main thing that I want to point out here is that for sequence classification, which we just did, what we did was we took the final output state from our LSTM, which is a contextualized representation of the entire sequence, and we slapped a perceptron on top of that to classify the whole sentence. If we want to do sequence modeling or sequence classification, where you want to classify each term in your sequence, the LSTM provides all of these output states as well. So all you do is slap a perceptron classifier on each one of those output states, and instead of classifying each sequence, you're classifying each element in your sequence. So to do this, there's really only one main change to the code base at all. I'm going to scroll down to here and just show you guys. Yeah, so it's on the screen. Can anybody tell me? Yep.
Next one first.
All right. Can anybody just tell me really quickly where I deleted like 3 characters. Does anybody know where the 3 characters that I deleted on here from the last notebook are? Here, I can make it a little bit bigger. What? Yeah, so this guy right in here. So the final output before was LSTM output of -1. So I was just taking that last hidden state. And now I'm just taking the entire LSTM output. And because this is just a sequence of a whole bunch of outputs, I can actually treat that kind of like a batch and just send that whole batch, if you will, through my linear layer and treat that thing as exactly like I'm sending a whole bunch of examples through a perceptron. So it's the same exact thing. And I've just gone from entire sequence classification to a part of speech tagging model by just changing a single line in my text, which I think is really powerful. So with that, I think that I'm going to be stepping on somebody's toes if I keep up, but I'll stick around for a few minutes for questions. Thank you for your time.